Welcome back to AI.Code.Cast. Today, we're taking a deep dive into a problem that, well, it might seem pretty simple at first glance, but trust me, there's some really clever stuff going on under the hood. We're going to be figuring out how to tell if a number is a power of 2.
It's a classic problem, really.
Oh,
And
absolutely.
it pops up all the time in coding.
Yeah, especially when you're like trying to really optimize for performance.
Exactly.
Squeeze out all the efficiency you can.
You hit the nail on the head. It's one of those foundational things that you might not think twice about at first, but then you start to dig into the efficiency side of things, how numbers are actually represented in a computer, and
Yeah, right.
that's where things get interesting.
Okay, so just to make sure we're all on the same page, we're talking about numbers like 2, 4, 8, 16, right? The kind of numbers you get when you raise 2 to some power.
Exactly.
Like, 2 to the third power is 8, that sort of thing.
You got it. And
Yeah.
the first thing that might come to mind is, well, why don't we just keep dividing the number by 2 until we hit 1? Or we realize it's not going to divide evenly.
Right, that's the brute force way, the kind of like straightforward approach. It would totally work. But I have a hunch there's a more,
Elegant way to do this.
there is.
Oh, I knew it.
And to get there, we need to tap into the magic of what's called bit manipulation.
Okay, bit manipulation. I like the sound of that already.
To really understand it, we got to think about how computers represent numbers, not in our usual decimal way, but in binary form.
Right, binary, the world of ones and zeros. So each position in a binary number represents a power of 2, correct?
Absolutely. Each position corresponds to a power of 2. Now, picture the binary representation of those powers of 2 we talked about. What kind of pattern jumps out at you?
Okay, let's see. So 2 is 10 in binary, 4 is 100, 8 is 1,000. Oh, I see it. They all have just a single 1 bit,
Yes.
with all the rest being zeros.
You nailed it. That's the secret sauce, the unique fingerprint of powers of 2 in their binary form.
That's pretty neat. And this is what opens the door to using bit manipulation to figure out if a number is a power of 2.
Okay, so instead of all that dividing, we can somehow use this single 1-bit thing. But how? I'm all ears.
There are a couple of really neat ways to do this.
Oh,
One of them uses what's called the Bitwise AND Operator. You usually see it written with an ampersand symbol.
okay, like the end symbol.
Exactly. Think of this AND operator like a filter. It only gives you a 1 in the result if both of the bits you're comparing in the two numbers are also 1.
Oh, right. Kind of like those logic gates from back in the day.
Exactly.
Okay, so how does this any thing help us with the powers of 2?
Well, here's the trick. Imagine you take a power of 2, any power of 2, and you subtract 1 from it.
Okay.
What happens to its binary form when you do that?
Let's take 8 as an example. So 8 in binary is 1,000. If I subtract 1, I get 7, which is 0, 1, 11 in binary. Huh, interesting.
Right. What do you notice?
It's like subtracting 1 flips that rightmost 1 bit to a 0.
Yeah.
And then it turns all the bits to the right of it into 1s.
You got it. That's the pattern.
So what happens if we do, like you said, the bitwise AND between the original power of 2 and this new number, the one we got after subtracting 1?
Let's see. Let's stick with our example of 8. So
Okay.
8, which is 1,000 in binary, AND 7, which is 0, 1, 11.
We get 0, 1, 0, 0, because that 1 bit in the 8 is lined up with a 0 in the 7.
Exactly. And guess what? This always happens when you're dealing with powers of 2.
Really?
Yep. This bitwise AND of n and n minus 1 will always give you 0.
Huh.
If and only if that n was a power of 2 to begin with.
That's really cool. So if we want to check if a number is a power of 2, we just do this quick n and d n minus 1 calculation and see if we get 0.
Exactly. And here's the best part. These bitwise operations, they happen super fast.
Fast. Like how fast?
We're talking constant time complexity, often written as O1.
01. Okay, so that means no matter how big the number is,
Doesn't matter how massive the number is.
this check will take the same tiny amount of time.
Yeah.
Wow, that's pretty powerful.
Right. It all comes down to working with the way numbers are actually represented at their core at the bit level.
Right.
And there's another equally slick way to check for powers of 2, one that involves zeroing in on that rightmost 1 bit.
Isolating the 1 bit. Oh, now you've got me really intrigued. How do we do that?
Well, that involves taking a little detour into the world of negative numbers and something called 2's complement.
2's complement. Oh, yeah, I remember that from way back in my computer science days, but a refresher would be great.
Absolutely. It's a way computers represent negative numbers, and it's actually simpler than it sounds. To get the two's complement of a number, you just flip all its bits and then add 1 to the result.
Okay, let's try that out with, let's say 8 again. 8 is the thousandth binary, right?
Right.
If I flip all the bits, I get 0, 1, 101.
Yep.
And if I add 1 to that, it becomes 1000 again. Wait a minute, that's the same as the original number.
You're right, they look the same. But here's the catch. The computer uses that leftmost bit as a sign bit. If it's 0, the number's positive. If it's a 1, it's negative. So even though those two 1000s look identical,
Right.
they're actually representing 8 and -8.
Ah, I see. The sign bit is the key.
Exactly. Now, how does this two's complement thing help us zero in on that rightmost one bit? That's where things get really cool.
Okay, lay it on me.
When you do a bitwise AND between a number and its two's complement, the only bit that'll survive in the result is that rightmost one bit. All the others magically vanish.
Wow, really? Can you show me an example?
Sure, let's stick with our trusty 8. We know its two's complement is a megajate, which is represented as 1000. Now, if we do a bitwise AND between 8, which is 1000, and its two's complement, also 1000.
We get 1000, you're right. Only that rightmost one bit is left standing.
It's like a spotlight shining right on that single bit.
So how does this tie back into the whole power of 2 problem?
Well, think about it. If we do this AND operation and the result is the same as the original number, that means the original number must have only had one bit to start with.
Which means it's a power of 2.
Bingo! So we've got ourselves another super efficient way to check for powers of 2.
That's incredible. So we have 2 different bit manipulation methods for solving this problem, and they both have, what was it, O1 complexity.
You got it. Constant time complexity, super efficient, either way you slice it.
But aren't they basically doing the same thing under the hood? Like, which one would you actually use in practice?
That's a great question. Both methods take advantage of that special property of powers of 2 where they only have a single 1 bit in their binary form. But there are some subtle differences. The NAND n-1 method, that one might be a bit easier to grasp at first.
This feels a bit more intuitive.
But the NAND negative n method, the one that isolates the rightmost 1 bit, that one can be more versatile. You might find yourself reaching for it in other bit manipulation scenarios.
So knowing both of them gives us more tools in our toolkit.
Exactly. Understanding both methods broadens your horizons in the world of bit manipulation. A world, might I add, that is full of elegance and efficiency.
I'm starting to see that.
Yeah.
Okay, let's recap for our listeners so far. We began with a straightforward but maybe a little slower way of repeatedly dividing by 2 to see if a number's a power of 2. Then we jumped into these 2 super efficient bit manipulation techniques.
Yep.
The first one, we check if NAND-n-1 gives us 0. And the second one, we see if NAND-n is the same as the original n. Both of these are blazing fast.
And elegant.
Yeah. And they open up a whole new world of possibilities for optimization.
Absolutely. And remember, understanding the why behind these solutions, that's just as important as knowing how to implement them.
Right.
Because it's that deeper understanding that lets you take these techniques and apply them to other coding challenges you'll encounter down the road.
This deep dive has really been eye-opening. I'm starting to see bit manipulation everywhere now.
It's like a secret code embedded in how computers operate.
Totally. But before we move on, I have one more question. We've seen how these tricks work for positive powers of 2.
Right.
But what if we throw a negative number or a really, really big number into the mix? Do these techniques still work?
Ah, an excellent question. And that takes us into some of the more subtle aspects of bit manipulation. Dealing with negative numbers means you have to be careful with that sign bit.
Right.
And for super large numbers, you might need to use special data types.
So there's always more to explore in the world of bit manipulation.
Absolutely. It's a fascinating journey of discovery, and the more you learn, the more you realize how much more there is to uncover.
Well, that's a great place to pause for now.
Sounds good.
We've covered a lot of ground today, from the basics of powers of 2 to the elegance and efficiency of bit manipulation. And to our listeners, don't touch that dial. We'll be back with more fascinating insights in just a moment. So it sounds like we need to dig a bit deeper into this 2's complement thing to really understand how it helps us with those 1 bits.
Right, let's break it down. We already tried it with 8, remember?
Yeah, we flipped the bits, added 1, and ended up back at 1000.
Exactly. And even though it looks the same as regular 8, it's actually representing n-8 because of that sign bit.
Right, that leftmost bit tells us whether it's positive or negative.
Now, the cool part is what happens when you do a bitwise ND between a number and its 2's complement. Think of it like this. Only the rightmost one bit survives this operation.
The rest just disappear.
Gone. Vanished. All those other bits become zeros.
Wow, that sounds almost magical.
It's pretty slick. Let's visualize it. Let's say we have the number 12,
Okay,
which is 1100 in binary.
got it.
Now, to get its 2's complement, we flip the bits, which gives us 0011.
Right?
Then we add 1, and we get 0100. That's the 2's complement of 12.
Okay, I'm following so far.
Now comes the fun part. We do a bitwise AND between 12, which is 1100, and its 2's complement, which is 0100.
And what do we get?
We get 0100.
Hey, that's just the 2's complement itself.
Right. Only that rightmost one bit made it through.
Yeah. I see. So it's like we isolated that one bit, kind of like shining a spotlight on it.
Exactly. And this is super useful for checking if a number is a power of 2. Remember, powers of 2 have only one bit in their binary form.
Right, right.
So if we do this AND operation with a number and its 2's complement and the result is the same as the original number, boom, we know it's a power of 2.
Because that means it only had one bit to begin with.
You got it. So now we have 2 powerful bit manipulation techniques to check for powers of 2. We can either use n AND n minus 1 and see if we get 0,
Right.
or we can use n again negative n and see if that gives us back the original n.
Both methods, super efficient, constant time complexity.
It's amazing how much we can accomplish just by understanding how numbers are represented in binary and how those bits can be manipulated.
I know, right? It's like a whole new world of possibilities opens up.
And the best part is, these techniques aren't limited to just checking for powers of 2. There's so much more you can do with bit manipulation.
Like what? Give me some examples.
Well, think about things like setting or clearing specific bits within a number. Imagine you have a program where you need to keep track of various flags or options.
Like settings in a game or something.
Exactly. Instead of using a bunch of separate variables, you can pack all that information into a single number, with each bit representing a different flag.
So like one bit could mean music on, another bit could mean sound effects enabled, and so on.
You got it.
Ah.
And then you can use bitwise operations to easily manipulate those flags. For instance, you could use bitwise AND to check if a particular flag is set, or bitwise OR to turn a flag on.
That's pretty clever. It's like having a super compact way to store and manage information.
And it's super efficient too, both in terms of memory usage and processing speed.
Bit manipulation is definitely a powerful tool to have in your coding arsenal.
Absolutely. It can make your code faster, more concise, and sometimes even more elegant.
Okay, I'm convinced. I need to brush up on my bit manipulation skills.
I encourage you to do so. The more you explore this world, the more amazing things you'll discover.
I'm definitely feeling inspired now. This deep dive has been a real eye-opener.
It's been a pleasure sharing this journey with you.
And to our listeners, we hope you're enjoying this exploration of bit manipulation as much as we are. Stick with us. We have even more fascinating insights to share in the next segment. You know, it's amazing to me how this seemingly simple idea of checking if a number is a power of 2 has led us to all these fascinating concepts.
It really highlights the beauty of computer science, doesn't it? How these fundamental concepts like binary representation and bit manipulation have such wide-ranging applications.
Absolutely. And I'm curious, are there other areas where bit manipulation is particularly useful?
Oh, definitely. One area where it really shines is when you're working with sets or flags. Imagine you have a bunch of different options or features that you need to track.
Like settings in a software program or...
Exactly. Or different power-ups a player might have in a video game.
Okay, I'm following.
Instead of using a whole bunch of separate variables to keep track of each option, you can pack all that information into a single number
How do you do that?
by using individual bits within that number to represent the state of each option. Think of it like a series of light switches.
Oh, I like that analogy.
Each switch can be either on or off, just like each bit can be a 1 or a 0.
So if we have, say, 8 different options, we could use an 8-bit number to represent them.
Precisely. Each bit would correspond to one of the options. If the bit is set to 1, it means that option is active. If it's 0, it's inactive.
That's pretty clever. So how would we actually manipulate these bits to turn options on or off?
That's where bitwise operations come in. Let's say you want to check if a particular option is enabled. You could use a bitwise AND with the mask that has only the corresponding bit set to 1.
A mask. What's that?
It's basically just a number that we use to isolate the specific bit we're interested in. For example, if we want to check the third option, which corresponds to the third bit, we would use a mask with only the third bit set to 1. So we'd perform a bitwise AND between our options number and this mask. If the result is non-zero, it means the third bit is set in our options number, meaning the third option is enabled.
That's pretty slick. And I imagine there are other bitwise operations we can use to, like, turn options on or off.
Absolutely. Bitwise R can be used to set a specific bit to 1, regardless of its previous state.
So to enable an option.
Exactly. And Bitwise XOR can be used to toggle a bit, flipping it from 0 to 1 or 1 to 0.
Wow. So we have a whole set of tools to manipulate these individual bits and control our options.
It's all about leveraging the power of binary representation and bitwise operations. And as we've seen, these techniques can lead to incredibly efficient and elegant solutions.
I'm definitely starting to see that.
Yeah.
Bit manipulation is a whole new world to explore,
Mm.
and it's clear that it has a lot to offer for programmers who want to write really optimized and efficient code.
It's been a pleasure diving into this topic with you.
Likewise. And to all our listeners, we hope you've enjoyed this deep dive into the world of bit manipulation. It's a fascinating subject with applications far beyond just checking for powers of two. So keep experimenting, keep learning, and we'll see you next time on AI.Code.Cast.